Good morning all. Today we can discuss about some problems related to electric potential due to spherical charge distribution. It may be solid sphere or hollow sphere. So see the first question. A point charge Q is placed outside a hollow spherical conductor of radius capital R at a distance small r. Of course, outside, that means which is greater than capital R from its center C. The field at C due to the induced charges on the conductor is. Okay. In the question, it is given that a spherical charge distribution is given. Of course, hollow spherical conductor simply given. It is an uncharged conductor. There is no charge on that. And the center is taken at C here. And a charge was placed here at a distance small r from C, that is plus Q. And now they are asking us to calculate the electric field at point C due to induced charges on the conductor. So really the total charge on the conductor, this spherical conductor, will be 0. But so because of this particular charge, if it is positive charge, then what will happen? Some negative charges will be induced towards the positive charge, and positive charges will be repelled, and they will just be on other side of the conductor. In this particular case, so finally, since it is a spherical hollow sphere, it is a hollow sphere. So what should happen here? In this particular case, or at point C, electric field finally should be equal to 0. So which will produce electric field here? There are two possibilities for electric field. One is due to the positive charge Q and due to the induced charges here. So first of all, if I consider, or if I want to calculate electric field due to the outer charge capital Q, E due to capital Q, E bar due to capital Q, how much it will be? 1 by 4 pi epsilon naught Q by distance square. What was the distance we mentioned from C to this point Q? So that is taken as small r. So electric field is 1 by 4 pi epsilon Q by small r square. Towards left it is. Why? Because both are, this is positive charge only, always electric field is away from positive charge. So that towards left it will act. But finally the electric field intensity at center should be 0, even due to any number of charges surrounding it. So there should be a charge here. There should be an electric field here due to the induced charge, which is equal and opposite to the electric field given by this particular charge. So E bar due to induced charge. So definitely it should be the same thing, 1 by 4 pi epsilon naught Q by R square, the resultant electric field due to induced charge, and towards right only. So, and in the question they are asking only electric field intensity due to induced charge. So only due to induced charge it will be 1 by 4 pi epsilon naught Q by R square. Okay, see again I will explain this question. A spherical body is given, hollow conductor is given, and it is having 0 charge on the surface. That means it is not a charged spherical surface. And at some particular distance from that, at a distance smaller from the center of the sphere, a positive charge is placed. So totally at the center of the spherical charge distribution, electric field will always be 0. And here what are the causes to give electric field at center? There are two causes. One is the positive charge placed at smaller distance, and the induced charge due to this positive charge, induced charge on the surface. In this particular case, if the electric fields due to these two factors should be equal and opposite, you have to understand. So that first we have taken electric field due to the outermost charge plus q, and the electric field due to induced charge will be equal and opposite to that electric field. That means the charge is induced on the sphere in such a way that the total electric field at center will be equal to 0. Okay, so this is the solution for the first question. Now, question number 2. A point charge q is placed at a distance of r from the center of an uncharged conducting sphere of radius capital R, which is less than small r. So the same information given in the previous question. The potential at any point on the sphere E is. Okay, potential they're asking us to calculate here. So the similar diagram was taken. What is that? A spherical charge distribution is given, which is uncharged here, and a small charge q is placed at this particular point at a distance small r from the center, and the radius of the sphere was taken capital R. And because of this particular charge, what will happen if it is positive charge and some negative charge will induce towards one side and positive charge will induce towards other side of the surface of the sphere. Okay, now in this particular case, on the surface of the sphere, they are asking us to calculate what we have to calculate here. To calculate potential. Okay, now due to induced charge, if you want to calculate the potential, since totally it is uncharged sphere, of course because of induction some charges will be on the surface, but total charge, if I consider, the total charge will be 0 on this one. So that potential due to spherical distribution, V due to spherical distribution will be 0. And what about V due to charge q? That is nothing but 1 by 4 pi epsilon naught q by small r at any point on the sphere. Not only, always you have to take the center as a reference. Okay, at any point on the sphere, the potential will be 1 by 4 pi epsilon naught q by r. Okay, so answer is 1 by 4 pi epsilon naught q by r. See here, because of induced charge, what is the total induced charge? And here, potential is just scalar. It is just sum of the potentials due to individual charges, and so that finally the total potential will be 0 only. But because of this particular charge, if I consider center as the reference here, then answer will be the general formula 1 by 4 pi epsilon naught q by r. Okay, now question number 3. A hollow metal sphere. A hollow metal sphere of radius 5 centimeters is charged such that the potential on its surface is 10 volts. The potential at the center of the sphere is. The hollow metal sphere is taken whose radius is 5 centimeters, and on the surface of the sphere the potential is given 10 volt. And we know that on a hollow sphere, inside the hollow sphere, electric field intensity will be 0 and potential remains constant. And that potential is equal to the potential on the surface at any point on the surface. So that very general formula we can use, and whatever the potential is there on the surface of the hollow metal sphere, the same potential it maintains at each and every point inside the metal sphere. Hence, the answer is simply 10 volts only. That means on the surface and on inside the surface at every point, potential is same, that is 10 volt. And the question number 4. A sphere of 4 centimeter radius is suspended within a hollow sphere of 6 centimeter radius. Okay, two spheres were taken. One sphere is having 4 centimeter radius, inner one, and outer one is having 6 centimeter radius. The inner sphere is charged with a potential 3 ESU when the outer sphere is earthed. The charge on the inner sphere is. Okay. Now, let me draw the diagram for this given information. So I can just draw here an inner sphere and an outer sphere like this. And the outer sphere is grounded. The outer sphere is grounded. That means potential at a point on the outer sphere will be 0 only. But what is the potential given on inner sphere? This is 3 ESU. It was given in electrostatic units. It is 3 ESU. Okay, here the potential should be 0. And what are the radii given for the two spheres? For the inner sphere, the radii was given 4 centimeters. And for the outer sphere, the radius was given 6 centimeters. Okay, now to calculate the potential at inner sphere, potential on inner sphere. For example, if Q is the charge on inner sphere which you have to calculate, then what will be the charge on outer sphere? So because of induction, so minus Q charge will be induced in the inner part of the outer surface. Okay, hence what is the potential due to this particular sphere at the same point on the surface? That will be 1 by 4 pi epsilon naught. General formula I will write here. That is 1 by 4 pi epsilon naught into Q by R. That means Q by 4. Next, the potential due to the outer surface, that will be again 1 by 4 pi epsilon naught minus Q, which is induced due to the charge on the outer surface of inner sphere. That is Q by 6. Okay, if you just take the difference, then it will be 1 by 4 pi epsilon naught into Q by 4 minus Q by 6. Okay, now this is equal to, of course, what is the potential on the inner sphere was given 3 ESU. When you substitute the values in electrostatic units, no need to write this coefficient 1 by 4 pi epsilon naught. In SI units only we have to write this 1 by 4 pi epsilon constant, but in electrostatic units no need to write this factor. So simply 3 ESU means that is equal to Q by 4 minus Q by 6, which is Q by 12, and 3 equal to Q by 12, and Q equal to 36 electrostatic units. So finally charge on the inner sphere will be equal to 36 electrostatic units for having that much potential on the sphere. Okay, now, and a small point here. Here, for example, here the charge is Q, and if it is grounded here, the total potential will be 0. Then always you have to take, or some charge will be induced here due to this particular charge only. So whatever the amount of charge here, the same amount in opposite side with opposite sign will be induced on the inner part. So that will cause some potential at this point. That's why we did like that. Okay. Next question number 5. A charge Q is distributed over two concentric hollow spheres of radii small r and capital R. Capital R is more. Outer one is capital R, and for inner one it is smaller. such that the surface densities are equal, the potential at common center is. Okay. So a charge Q is distributed given. That means total charge is given, total charge given is Q. Then we can just write here total charge is Q, which is divided into two parts, of course Q1 and Q2, which is given on the in the two spheres. So let me consider again the two spheres here, inner one and outer one. Just a minute. This is inner sphere, let me consider, and this is some let me consider this is inner sphere. Okay. Now the radius of the inner sphere given is small r. The radius of outer sphere is given capital R according to the question. And let me consider the total charge is divided into two parts. Q1 is given to the inner sphere and Q2 is given to the outer sphere. Okay. Now one more information given. What is that? The surface densities are equal. What is the formula for surface density? Symbol for surface density? Sigma. Sigma 1 equal to sigma 2. Sigma 1 means charge by area. Surface area will be 4 pi small r square equal to Q2 by 4 pi capital R square. By solving this, Q1 equal to 4 pi and 4 pi will get cancelled. Q2 into small r square by capital R square. Let me consider this is equation 1 and this is equation 2. So by substituting equation 2 in equation 1, so Q1 plus Q2 equal to capital Q na. In place of Q2, Q1 if you write this, Q2 R square by R square plus Q2 equal to capital Q. Q2 you have to find out finally here. So if you take Q2 common here, small r square by capital R square plus 1 by taking LCM, small r square plus capital R square by capital R square into Q. And finally, Q2 can be written as capital Q into capital R square by capital R square plus small r square. In the same way, if you calculate Q1 from this equation, Q1 is nothing but this one. In second equation, if you substitute Q2 value, then you will get capital Q into, this is square only, capital Q into small r square by capital R square plus small r square. And finally, we got the values here for Q1 and Q2. And small r, capital R, we know that. Now you have to calculate finally the potential at common center. Potential due to first sphere and also potential due to second sphere you have to calculate. Okay, I will just go through that now. What is the formula for total potential here? This is nothing but potential due to first sphere 1 by 4 pi epsilon naught. I will take common in both the cases. Due to first sphere it will be Q1 by small r plus due to second sphere it will be 1 by 4 pi epsilon naught into Q2 by capital R. If you just substitute here the values of Q1 and Q2, if you substitute Q1 value, one smaller and smaller will get cancelled, and finally you will get Q into small r by capital R plus small r plus Q into capital R by capital R square plus small r square. Now, which you can take common here, Q by Q can be taken common here. 1 by 4 pi epsilon naught into capital R square plus small r square. Then finally you will have capital R plus small r. So this is the formula for potential at center. Okay. So just we calculated charges on each sphere in terms of the given symbols, like capital Q, small r, and capital R. Small q, Q1 and Q2, just we considered for our convenience. So, but in the question, the information given is capital Q, small r, and capital R. In those terms, first we have written the Q1 and Q2 values. Then finally, we just have written the very familiar formulas for potential. Okay. Next, question number 6. Here, a solid conducting sphere, is taken, having a charge Q is surrounded by an uncharged concentric conducting hollow spherical shell. A solid sphere is taken whose charge is capital Q and it is surrounded by, that means outer sphere is an uncharged concentric conducting hollow spherical shell. A hollow sphere is taken. Let the potential difference between the surface of the solid sphere and that of the outer sphere of the hollow shell will be V. Okay, potential difference between the two shells was given. If the shell is now given a charge of minus 3Q, the new potential difference between the two surfaces is. Okay, just I will draw here the diagram for the given information. So just they have taken here a shell here and a small sphere is also taken inside. Of course, this is a solid sphere. Let me consider this is a solid sphere. And the outer one is shell only. And here the charge is given Q. And here it is uncharged shell it is. Okay. So when an uncharged one is there, so what will happen here? A small charge will be induced here. That is minus Q and here plus Q. Of course, due to minus Q, some potential will be there. Some minus Q will be induced here. Now, the question is the potential difference between this point and this point, these 2 points, is given V. Okay. Now, generally, the potential difference or potential due to inner one. What is the general formula? For example, inside the for inner sphere the radius is small r, and for the outer sphere the radius is capital R. What is the potential at inner sphere? It is 1 by 4 pi epsilon naught Q by small r. Okay. And due to this particular one, due to this particular charge, here the potential is 0 only. Okay, here the potential will be 0 due to this one. Why? Because total charge is 0 here. So, and what is at outer surface? At outer surface, the charge is 0, total charge is 0 here. So that here we don't consider, just a minute. So with very much simple steps, we can solve this. No need to write all this formula also. That is, see here, at this particular point, the potential is due to inner solid sphere and also the outer one. Of course, initially at the outer shell, there is no charge, that is different. But generally at this point, potentially due to inner one and outer one. But at this point, But at this point, we take the potential due to only inner one here. Why? Because at outer part, the outer sphere, the charge is 0. But the information given is in the question is some charge minus 3q is added. Some charge minus 3q is added here. Whenever this much amount of charge is added on the outer sphere, in that particular case, this will cause the potential at this part of the sphere and also at this part of the sphere, since it is a shell. Since it is a shell only. So what will happen? The potential at every point due to this extra charge will be same. That means at this point and at this point, at these 2 points, the potential due to this particular excess charge will be same. That means that will not cause any extra potential difference. Hence, the total potential difference, even an amount of charge is added to outer sphere, the extra potential difference will be the same, because it gives the same excess potential at the 2 points. So that potential difference is again V only. I hope all of you understand the explanation. See here, where an extra amount of charge is added at the outer sphere, that will cause the same potential at these 2 points, because at any part of the shell, the potential remains constant on the surface or inside. So if it gives same potential, the potential difference does not influence, na? So the potential difference will be again V only. Okay. Now, question number 7. Some 3 concentric metallic spheres A, B, and C have radii A, B, C, small a, small b, small c, and surface charge densities on them are sigma, minus sigma, and sigma, respectively. The values of VA and VB will be. So finally, they're asking here the values of potential at A and potential at B. Okay. Now, just a minute. So 3 spheres were taken here. Just I will draw the 3 spheres here. Let me consider all the concentric. If you see the diagram, there will be small deviation, but you please keep in your mind that all the spheres are concentric spheres only. And here, the radius of first sphere is given A, and the radius of second sphere is given B, and the radius of third sphere is C, and the sigma values are sigma, minus sigma, and plus sigma respectively for the 3. And that is the information given here, and the names of spheres ABC given. Now they are asking us to calculate potential at A. Potential at this particular sphere will be due to first one, second one, and also the third one. Due to the first sphere, it is on the surface of the first sphere. So what is the general formula? 1 by 4 pi epsilon naught Q on that particular sphere by radius. And due to the second sphere, the potential at this point, how much it will be? Whatever the potential on the surface of that sphere, that only will be at every point inside. Hence, that will be 1 by 4 pi epsilon naught QB by radius B. And due to the third one, it will be 1 by 4 pi epsilon naught QC by C. And of course, this is having a negative charge density. That means negative charge will be here and it will be positive here. In this particular case, 1 by 4 pi epsilon naught is common. And simply, we can write here charge by A minus charge on B by B plus charge on C by C. Charge is nothing but, in terms of density, they are given density equal to charge by area, charge equal to density into area. That means that is sigma into 4 pi r square. That means 4 pi a square by A minus sigma into 4 pi b square by B plus sigma into 4 pi c square by C. 4 pi can be taken common and 4 pi and 4 pi will get cancelled. Sigma is also common here. So finally sigma by epsilon naught into, so A and A will get cancelled. A minus B plus C. Okay. So this is the potential at point A. And now we can calculate potential at point B. I will just erase this. For potential at B, due to inner sphere, one inner sphere is there. Due to inner sphere at outer point you have to take. So due to the first one, this is 1 by 4 pi epsilon naught into Q on A by B here. The distance from the center to the second sphere will be B. Next, minus, for the second sphere it is only on the point, on the sphere the point is. So QB by B plus QC by C. Again, in the same way, if you substitute sigma into 4 pi r square in case of QA, QB and QC, then you will get sigma by epsilon naught into, this will be A square by B minus B square by B plus C square by C. And this will be sigma by epsilon naught into A square by B. Nothing will be cancelled here, minus B plus C. So this is the answer for potential at point B. And the first answer will be, in the given options, a small mistake is there. So A minus B plus C should be there in case of first potential. And now the question number 8. A small ball of mass 2 into 10 power minus 3 kg having a charge of 1 microcoulomb is suspended by a string of length 0.8 meters. Another identical ball having the same charge is kept at point of suspension. Determine the minimum horizontal velocity which should be imparted to the lower ball so that it can make a complete revolution. This is just like circular motion, vertical circular motion related. Now, for example, here point of suspension is there, and here a wire is placed, and where at the bottom part of the wire again some charge is placed. Charge and mass values are given. Let me take M and Q here. So when some velocity is given at this point, of course these here you will have electrostatic repulsive force. And then what will happen? What should happen here? It should make a complete. It should follow a complete circular path like this. And to have that, they're asking us to calculate here whatever the velocity should be given. Let me consider this is bottom point is A and upper point is B. Okay. In this particular case, we can write whatever the kinetic energy given at the bottom part, that is half mv square, of course VA square. It is equal to some kinetic energy remain when it is at upper part only. So otherwise it will just fall down, so that it also will have some velocity plus, and the remaining will convert into potential energy. Potential energy is mgh na, m into g into, if the length of this one is L, this point rises from here to here, totally 2L height it rises, so that mg into 2L. Let me consider this is equation 1. And also some for having or to complete a rotation, the minimum velocity to have here, the condition is what are the forces acting in upward and downward directions? In downward direction, mg is acting. In upward direction, some electrostatic repulsive force is acting because these two are similar charges. And the resultant of these two forces will cause a rotation there or a centripetal force there. Of course, tension will be zero at upper point. So we can write here mg minus electrostatic force is equal to their velocity mv square by L. Their velocity is vb. This is equation 2. And if we substitute all these values, what is mass given in the question? Mass given is 2 into 10 power minus 3 kg into g is 10, and electrostatic force means 1 by 4 pi epsilon naught into q1 q2. Each charge is given 10 power minus 6 coulomb. So q1 q2 means q square, that is 10 power minus 12 by length L is given 0.8 meters whole square, that means 64 into 10 power minus 2. This is equal to, again mass is 2 into 10 power minus 3 kg. Vb square we don't know. First you have to calculate that. By L is again 0.8. By solving this particular equation, you finally will get here, of course, I will solve this 2 into 10 power minus 2 it is. And this will be, finally, just you try to solve that. And the answer is nearly Vb square is 38 by 16 we got. That is nearly 2 point something, 2.4 something you will get. That is the value of Vb square. But finally you have to calculate Va square. Na? If you substitute again the formula or say value of Vb square in the first equation, then you will get the answer for Va square. And Va square nearly we got 34.4 and Va is nearly equal to 5.8. Okay, 5.8 meter per second. Okay, for having complete rotation, first of all you have to take two equations. One is energy conservation. Whatever the kinetic energy given at the bottom part, that is equal to the kinetic energy remain in the upper part plus the potential energy change, that is mg into 2L. And in the same way, which causes the rotation and tension will be zero there, then the resultant force, the resultant of two forces, gravitational and electrostatic force, that difference causes centripetal force there. Okay, so in that way, second equation we can write, and the given values if you substitute, first we will get the answer for Vb, then finally we'll get the answer for Va, which is equal to 5.8 meter per second. Next, question number 9. A sphere of radius r has uniformly distributed charge density rho. There is a spherical cavity as shown in the figure. Some point I think it was missed here. As shown in the figure, has center at C. Correct one. Has center at C. It is given that AB equal to small d, OC equal to L, and the angle between OC and AB is alpha. Find the potential difference between A and B. Okay, here the diagram was given. The similar diagram we can copy. Okay, I will draw it again. The diagram here given here is a sphere is taken where there is a cavity at some part here, and this is the center O, this is the center O, and the center of the cavity is C, And here 2 points were taken, B and A, point A and point B, and and OC is given, this length OC is given length L only, and here the angle is given alpha between this OC and the AC. They are not perpendicular, there is some angle, there is some particular angle there. Now they are asking us to calculate potential difference, and initially the total charge density is given rho here. In this particular case, first of all, let me consider this is equal to, this is particularly equal to the complete sphere, complete solid sphere minus a small sphere here. So if the electric field due to this sphere minus electric field due to small one which was removed from that part, so this is this will give the same answer for this question. So that I consider this is the first and second one, and first you try to calculate electric field due to intensity due to the first one. What is the electric field due to intensity due to the first complete sphere? That is simply rho r by epsilon, rho r by epsilon. But you have to calculate at one particular point. Let me consider a single point is taken, A or B, any one point only you consider first. Let me take it is B. Then what will be this? So this will be O like this. Here the center will be C and the point is B here. In this particular case, what is general formula is rho r by 3 epsilon naught for electric field due to this sphere. So rho r by 3 epsilon naught means rho by 3 epsilon naught into, in place of small r, we can write OB bar. And for electric field due intensity due to the small sphere, that also will be rho by 3 epsilon naught into here CB. And the final answer for this particular sphere is the resultant of difference between these two. That is rho by 3 epsilon naught into OB bar minus CB bar. So OB bar means this one, CB bar means this one. OB bar minus CB bar, in vector form it will be nothing but OC bar. So that will be rho by 3 epsilon naught into OC bar. So this is the electric field intensity, resultant electric field intensity at point B. Okay. And at the same time, you have to calculate potential difference between 2 points along this particular line. So to calculate that, now again, I will just erase some part here. So to calculate the potential difference between 2 points dV, you can simply write minus integral E bar dot dr bar from where to where? From A to B only or B to A only, whatever it means. So this is equal to minus integral. What is E bar given? Rho by 3 epsilon naught into OC bar dot dr bar. Dr bar means from A to B, whatever the distance is there. So what is the angle between OC bar and dr bar? This is OC bar. If you just extend this, here the angle will be 180 minus alpha. If this is alpha, this will be 180 minus alpha. So angle between OC bar and OA bar will be 180 minus alpha. So this will be minus integral rho by 3 epsilon naught into OC into dr into cos of 180 minus alpha. Dot product is there, na? So AB cos theta, OC into dr into cos theta. The angle between these two is 180 minus theta. Hence we have written here cos of 180 minus theta. What is cos of 180 minus theta? That is simply cos theta only, na? So here you can write rho by 3 epsilon naught is constant. OC, of course, OC is given L only. That is also constant. Cos 180 minus theta, cos theta. That is also fixed here. Integral dr. Integral dr means distance from B to A only, na? What is the distance from B to A given? That is simply small d given. In the question it is given that that is equal to small d. So finally rho L small d cos theta by 3 epsilon naught. So this is finally the potential difference between point A and point B. Okay. Now, question number 10. As shown, a solid spherical region having a spherical cavity whose diameter r is equal to the radius of spherical region that has total charge q. Find the potential at a point P which is at a distance x from C. In this particular question, it is given that, of course, here also one diagram was given. I will just draw here the diagram. These are all very much important model questions for JEE mains. See here. The sphere was taken like this. And this one. And we can draw here another sphere whose radius is half of this. Please imagine that it is a proper sphere of radius r by 2 only. And because this total radius is capital R given, that's why. And this is having only the half of the radius of the bigger one. And if you want to calculate potential at point P, which is at distance x from the center. Okay, and as shown, a solid spherical region having cavity. So with this cavity only the charge is q. That means after removing this sphere, this is not q. So after removing this particular sphere, then only for the remaining sphere only the charge is q given. Okay, in that particular case, you have to calculate potential. And you can just imagine this is nothing but when there is complete sphere, the potential you calculate. When a small part of the sphere, whatever the removed part is there, when that is there, you can calculate the potential. Then the difference between these two will be the potential due to this remaining sphere. I hope all of you understand how to solve this. Now you see this. To calculate that, first of all, you try to calculate potential due to the complete sphere. For the complete sphere, just a minute. V for complete sphere, if there is, really there is not a complete sphere with whole charge, complete solid sphere is not there. So for the, because of that, it will be 1 by 4 pi epsilon naught. For the complete sphere charge you have to calculate, but only charge is given for some part. How much part? Q by 4 by 3 pi r cube minus 4 by 3 pi r by 2 whole cube. For this part only charge given, total charge by this volume into the total volume if I consider. For that, how much it will be hard to calculate. This is the total charge if complete sphere is there by what is the distance from this sphere to the point x only, and what is the potential due to removed part. This is equal to, again, 1 by 4 pi epsilon naught into, according to the given information, this is q by 4 by 3 pi capital R cube minus 4 by 3 pi into r by 2 whole cube into the removed part is very small. That volume is 4 by 3 pi into r by 2 whole square only. So whole cube only. By what is the distance there? It is not on the axial line for the small part. For the small part, it is along the perpendicular line at the end of the sphere. So the total distance can be taken as root over x square plus r by 2 whole square. So, and finally, if you want to calculate potential due to the whole part, you have to take the difference of these two equations. And you simply see here 4 by 3 pi and 4 by 3 pi will get cancelled everywhere here. Here also they will be cancelled. So if I take q by 4 pi epsilon naught common in the whole equation, then 4 by 3 pi will get cancelled at everywhere, every point. That will be 1 by r cube minus r by 2 whole cube means r cube by 8 into, in denominator only, x minus, here also q is taken common already, and in numerator there is r cube by 8 by, in denominator, r cube minus r cube by 8 into, again in denominator you have root over x square plus r square by 4. Okay, and I think r cube also will get cancelled here, na? 4 by 3 pi r cube also will get cancelled. So simply you can write 1 only. 1 minus 1 by 8. Here also r cube will get cancelled. And this will be q by 4 pi epsilon naught into 1 by 1 minus 8. That will be 8 by 7x. 8 by 7x minus 1 by 8 by 1 minus 1 by 8. That means it will be 1 by 7, I think. 1 by 7 it will be. 1 by 7 root over, you can write here by taking LCM here, 4x square plus r square by 4. For if I calculate root for 4, it will be 7 by 2. 7 by 2 into x square plus, sorry, 4x square plus r square. So you can rewrite this equation according to the given options there. Okay, so this is the final answer. So just we have taken here, if complete sphere is there, we just imagine, and a small part if removed, that part separately the potential we calculated. So the difference only we calculate. Okay, see here, q is not given for the complete sphere. Q is given as charge for the sphere after removing some small part. So that's why we did like this. Okay, now